Thank you, Anthony. Thank you, first of all, to the local organizing committee for allowing me to present this work here. I work at the Institute of Astronomy at UNAM here in Mexico. And today we'd like to talk about the self-regulation of star formation at kiloparsec scales. So let me start by commenting something that we all know, that is that we have found, or people have been found using CO data, that at kiloparsec scales, or what we call local scales, and the star formation rate that we derive using the H-alpha emission is strongly correlated with the mass of the molecular component of the ISM. So there have been a lot of efforts trying to understand what is driving this tight relation between the molecular gas and the star formation rate. So on the one hand, we could have local condition of the ISM, like gas density, molecular gas fraction, or what we call the midplane pressure, or hydrostatic midplane pressure. Also, the global conditions of the galaxies could be of the host galaxies could be responsible, or could be lead to this relation. For example, the self-gravity, the gas dispersion or shear, or also the Coriolis force. But using the optical data, we have also found that there is another strong correlation between the star formation and the stellar mass density. So as some of you have already heard in the previous talks, what we call the local star forming main sequence. So as you can see, as you have seen in global scales, this tight relation between the star formation and stellar mass. At local scale, using large sample of integral field spectroscopy data, we also observe this tight relation between the star formation rate density and the stellar mass density. So we would like to understand what is causing these so-called scaling relations between the star formation and different components of the baryonic mass. So we try to understand this question, to answer this question using samples of IFU data. So before I move on to our results, I just want to mention that when we want to understand or sampling, have a good sample of galaxies and trying to answer questions regarding to the entire population of galaxies in the nearby universe, we need to remind ourselves that we have to consider galaxies or samples that are beyond what we call the cosmic variance effects, to overcome these cosmic variance effects. And you can see here in illustrious TNG simulations that once you get in a small volume of galaxies, let's say 15 megaparsecs, you may have, let's say, broaden or shift the actual measurements that you have from properties. For example, here I'm plotting the specific star formation rate. So in order to overcome, and as I mentioned, to have a really representative population of galaxies in the nearby universe, you need to sample further out. You need to sample at least galaxies that are beyond 20 megaparsecs and below 100 megaparsecs. So there have been different studies trying to explore these properties, different studies. One of those that I'm going to use and show you here is what we call the EDGE-CALIFA survey, which some of you already heard. So this survey, it's a study using Khalifa data, so IFU data from the optical. We have 126 galaxies, and from those galaxies, we have also measurements of the CO data. So we have a CO data cues from KARMA, so we have the CO distribution of these galaxies. And with this data, we want to explore this relation of the baryonic mass. So in order to do that, well, we have galaxies that we have the maps, the spatial distribution of the CO. That's from the KARMA data, but also from the optical, we have the stellar mass density, as you can see here, and also the H-alpha emission. So for this sample, what we have is a total of 96 galaxies that we call star-forming galaxies, and you can see here from this plot. But for each of these galaxies, we have, or in total, we have around 5,000 star-forming regions. And as you can see here in this star formation mass plane, we have a wide range, we cover a wide range of properties for this sample in comparison to other spatially resolved samples. So what we did with this is to derive what we call the star formation rate pressure relation at kiloparsec scales. Basically, what we found with these relations of this pressure is basically the classical derivation from Elmegren, which correlates both components of the baryonic mass, the stellar and the molecular component. So we find that this is the tightest star forming relation at kiloparsec scales, and the reason we're claiming that is because we find a large correlation factor, larger than individual correlation with individual components of the baryonic mass. We have a smaller scatter that we find here, and basically the slope is close to 1. So what we think is that what we are observing here is the local balance between the gravitational potential that is trying to push looking at the plane, push the material to collapse, versus the feedback from newly born stars. So this is giving you what we call, or what we think that at kiloparsec scales, the star formation rate is a self-regulated process. So as I mentioned, we compare this with different, with other more well-known scaling relations. So here is the result of star formation in sequence, as I told you before. And here is the result Schmidt-Kennicott relation. So you have the star formation rate here in the y-axis, the stellar mass density, and the molecular gas mass density. So we color code these relations with respect to each of these parameters. So here is color coded with respect to the molecular gas, and here is color coded with respect to the stellar mass density. So what you can see here is that it appears to be significant secondary correlation, so to speak, with when we color code these relations. However, if we color code the same now this pressure star formation relation with the molecular and the stellar mass density, we don't seem to find any significant secondary correlations as we see here. That's very obvious when you look at, you compare these two plots. So we further explore this. We explore the residuals of these scaling relations. And what we find is that you may have a strong correlation among the residuals, but those correlations could be induced and they may not have a physical explanation. I encourage you to see this article from Sebastian Sanchez, 2021, where we make a further exploration of the impact and having residuals that correlates with these different scaling relation. And the implication for this is that this could be, this could be misleading in the sense that you may have a strong correlation with the among the residuals of these scaling relations, but in fact, what you are finding is a strong correlation between the residue induced by the errors of the residuals or the statistical distribution of the residuals. So this is something very important to keep in mind. And as I mentioned, you can have, since you have a large sample of galaxies, you can also explore what is the impact of integrated properties in these local scaling relations. So that's something that we did also in this study. So we have the impact of the global parameters in this star formation pressure relation. The first thing that we did was to explore how this relation change when you have, well, for the different total stellar masses. We seem to find a slightly anti-correlation between the residuals and the total stellar mass, but once you try to see if this is a secondary parameter for reducing the scatter of this scaling relation, we don't seem to find a significant impact of the total stellar mass. We have also explored how this change with respect to morphology. With respect to morphology, and what we find is that we may see some trend, having that more early type galaxies tend to show a lower or negative scatter in this relation. We have to be clear here in the sense that we have a small sample of elliptical and S0 galaxies. So we would like to have a more sample of spatially resolved data to really prove this portion here and this morphology being for this sample, for this scaling relation. But another way to try to say what is driving this tight relation is using what is called the momentum injection per unit mass. So basically, this is just observationally speaking, this is basically the ratio between the star formation rate density and the pressure. So what we did here, what is commonly done, is to explore how this ratio varies with the pressure, right? So as you can see here, this is our sample. We color code these points by the H-alpha equivalent width. So basically, the H-alpha equivalent width is telling you the star formation activity. Since we are selecting only star forming regions, not we don't using regions with lower equivalent width lower than 6 angstroms. So we are confident that those are indeed star forming regions. So what you can see here very, very clear. So actually, this is the median distribution of this, the median point of the whole distribution. So what you can see here is that for the blue points, for the active star forming regions, the momentum injection increases with the pressure, right? This is clear from this plot. For the low activity star forming regions, we have, let's say, a wider distribution, wider points, but all of them are show for a given pressure, you have higher momentum injection for these low activity star forming regions. We can also compare it with values with the literature. So that's something that we do here. So this contour represents the values from the FANG survey that has a better spatial resolution, but the sample is smaller. So you still can see here that this trend that we see for active star forming regions holds. So the momentum injection increases with pressure. And we also have integrated measurements from galaxies that are highly disturbed. So that's called the dynamo galaxies. And it's still this relation, this trend holds in the sense that this momentum injection, even for these highly disturbed, high star forming galaxies, we still see this clear trend. So again, we try to see what is driving this tag relation, what is driving this self-regulation. So what we did here is to plot these values estimated from simulations and from the literature. So basically this green line represents the injection from supernova explosions, and this purple line represents the injection from supernova explosions, but also adding a component of stellar winds. So what we find is that for a large fraction of these star forming regions that we call active star forming regions, this momentum injection can be explained by the combination of supernova explosions and winds. But we cannot rule out that there. Thank you. We cannot rule out that there are other mechanisms that can be driving the self-regulation. In particular, as you can see here, for these regions of low activity. So there could be either that we are we need to take into account another mechanisms for this momentum injection, or that here is also something that we need to consider, that we are due to the spatial resolution that we have, we may include for these regions H-alpha emission that is not directly from star formation. So here I just leave my conclusion. So we need a proper sample of galaxies. In particular, we require large sample with the spatially resolved CO. We also found that the kiloparsec scales in the nearby universe, the star formation is a self-regulated process. And we think that the main responsible for this self-regulation is mainly supernova explosion and stellar winds. So I leave you with this. Thank you.
Thank you very much. Thanks for keeping on time. Any questions? Garcia?
Yes, a quick one. Thanks very much for the nice talk. The observations that are missing in CO, are they missing because you never got data or because these are not detected?
It's a combination of both. So on the one hand, we require more CO data, but especially resolved. But as you can see, as I showed you before, it will be also nice to see what is happening, for example, in the disk of those let's call early type CO, SO, SA galaxies. So where you have a bulge, but you also see clearly a disk, and you have CO emission in that disk. So we want to see what it may causing, if there is any difference or morphological difference, for example, in these scaling relations. But I will say it's a combination of both.
All right, thank you.
Thank you.
A question from me. How about our own galaxy? Clouds in our own galaxy, where would they fall on this parameter space?
So what we think is that, so I'm not exactly sure, I mean, what is happening in our galaxy. That's something that we are hoping to address with the new facilities like SLOAN 5. So local volume mapper is aimed to do precisely this kind of studies, because we have the CO, we have and we are going to have the optical mapping of regions within our galaxy and in very, very nearby galaxies. But what we have seen from the literature is that these kind of relations are very, let's call it statistically or stochastic, in the sense that, as you see here, we're integrating, in both time and space, in the sense that in time we're picking up the star formation from hundreds of mega years, and especially because we're integrating around a kiloparsec scale. So the combination of these two effects, it's what we think is leading to these kind of tight relations. And you have seen different works, for example, Kruges in 2019, the Nature paper, where you see how if you consider larger apertures in galaxies, so once you have like a kiloparsec aperture in a galaxy, in a very well-resolved galaxy, you start to see this kind of spatially similarities between the CO and the H-alpha emission. But if you go to smaller scales, you start to see that they separate with each other. So that's something that we are seeing. I'm pretty sure that once we go to these sub-kiloparsec scales at here in the nearby galaxy, using data from FACS, for example, we will start to see really, for example, the contribution from stellar feedback, But in that case, you will see like these shells of CO, and that in that case, this kind of scaling relation will tend to break.
Okay, thanks a lot. Thank you.